Morning. Can start. Have any questions on the previous lectures? Homework. I also published first lab. You've seen that on Canvas. Do you see it on Canvas? Canvas, the submission in about 2 weeks. More questions about previous lectures? Well, so the typical way any story should go is practically by starting with something mysterious, something weird, something unexpected, and then you have some twist in the story, and then you get punchline of the story to make it interesting. So in science, interestingly, everything the opposite way. We're starting with the punchline. We give all of the information immediately. We provide everything you need to know from the beginning. It makes things more boring in a way. But for people who don't have time to learn and to do anything, this is the way to go. So this is how most of the lectures go. I hope to give you immediately the idea where we are going, what we will be doing with that from the beginning, and then we start the story plot. And then we describe like how we get there. Again, I don't know if you prefer one way or another, but for people who don't have enough time, and in all publications and papers, you will see exactly the same approach. You have abstract, which is saying everything this paper is saying, and you don't even really need to read it if you don't need all of the details and specifics. You can know everything from that one paragraph where the author state everything you need to know about that paper from practical perspective, and only then they start to describe methodology, results, details. So the topic of the story is length, volume, area, all the things, and their generalizations. And the punchline here is that we are getting practically determinants, because determinants will generalize all of these notions all together, and this is where we are going with that. So it will not be clear from the initial half of the lecture, because we will talk about these particular things, which are lenses, areas, and so on. But later we will get why all of that is just that's what the meaning of all the things are. And previous time, like at the end of the lecture, I showed you some interesting, hopefully interesting, tricky thing, which is telling you a little bit about what distance is and your understanding of what distance is and what length is, in a sense. So just to summarize the previous lecture on the matrices, we will need to know. So we talked about transpose, we talked about diagonal matrices, identity matrices, adding and subtracting different matrices multiplied by scalars, multiplying matrices, vectors, all of that stuff. We talked about all of the dot products with vectors. We talked about how to define multiplication between two matrices, when it is multiplied, when the inner indices are equal, and outer indices are telling you the result dimensions of the matrix, multiplication of two matrices. And then we talked about solving system of linear equations, talked a little bit about LU and how to invert matrix with LU approach without having to go through all of these computationally difficult determinants. You need to remember also that AB is not equal to BA in matrices, which is extremely important property. It's not commutative, you cannot switch the order of matrices. And the only way to solve any kind of equations with matrices is to multiply from left or from right by inverse of that matrix if it exists. And there are properties when you can say it exists only when determinant of that matrix is not zero. Or you have some other properties also which are equivalent to the same thing. Okay, so this is just a reminder on the previous lecture. But now we start talking about any questions on that part. Remember all of the basic matrices start part. Okay, so what is length or distance? So first of all, length and distance are not exactly the same. In regular language, you're using length and distance interchangeably in many cases, but they're not exactly the same. And we will talk about also something which is called mathematical distance metric. And this is also not the same as the regular distance that we use in everyday life.
because something might be distance, but not really metric mathematically. And we will define all of the things. But before that, just to show you again that example of understanding of how we understand distances and what might be a problem with distances. This is an example that I showed previous time. And in that example, you have the triangle, and obviously A is shorter than B plus C. But if you convert that midline projections and you get exactly the same lines here, so you see, so AB and equals to the red segment up to C, and AC equals to segment B to the corner. So if I go Z trajectory on the dotted lines, it's exactly like going on the red trajectory, right? Same exact length, same exact distance that I need to walk. So if you go that step, you get that B1 plus B2 plus C1 plus C2 is exactly like B plus C. And it is obviously longer than A, okay? Because hypotenuse is always shorter than the sum of the two sides, right? From geometry. But I can do that multiple times, and then after a few steps, you get to whatever is closest you want to the line A, and then the question became,
So it's the same distance or length or whatever you call it, okay?
it's kind of, I can get as close as you want to line A, but the length seems to be much longer. So what is going on? Like, is there any trick in that thing? Have I missed some detail here? What happens? Do you think they're equal lengths? Obviously not.
Taking the vertical and horizontal and
Yeah,
segment.
but they are kind of closer and closer, and if you go like infinite number of steps, they become indistinguishable.
The eye maybe, but it's still there.
On microscopic level, yeah, but it's like microscopic differences in length are not real. Right? If you're looking on these two sides, they are much longer than
that line, right? But here it seems to be like less long. Is it?
Probably still the same length.
It's still the same length. Okay. So there is no trick in that exercise.
okay, there is nothing tricky here. It's coming to our philosophical understanding of what length is. Okay.
So lengths and distances you can define only when you have some sort of ruler, which is straight segment. And you subdividing whatever curve or distance that you need to go into these tiny pieces of straight segments. And then you adding them together, those distances together, and then you get particular distance that you need to walk. And you can only approximate it, which means that this distance will depend a lot on the type of the rulers that you choose. Depends on the ruler, you will have different lengths, different distances. Ruler matter. So how big is your ruler? Like if you using as your measurement like 1 mile, then this is how you do it. But if you're looking on particular details of the trajectory on much smaller scale, you might get lengths from that straight segment to almost infinity. Okay, you can get any length, and it will be as close as possible to your original 1 mile length. And this is how we look at that on the map, for example. So typically, if you go like to Wikipedia, it says that all of the border with Mexico would be almost 2,000 miles. What does it mean, 2,000 miles? Measuring with what?
Miles.
You measure that in miles, which means straight segments of 1 mile. Okay, so if you measure that with straight segments of 1 mile, you will get approximately 2,000 miles. Okay, but if you measure that with regular ruler, it will be much longer than that if you go specifically on all the twists and turns. Okay, if you go that on microscopic level, like sand type of level size, okay, you can get like millions of miles if you want to. Okay, it depends on how you go around the sand. Okay, go on particular trajectory. But on mile level, it will be still same thing, right? So it depends on your size of the ruler. You will get completely different lengths which are typically people do not think about length that way. They think about, oh, I know what length is, and like how I measure it, and this is particular length, because we think in straight segments. We do not think in zigzags. Okay, so we have kind of mental problem in measuring lenses. So we need to define that mathematically more precisely. What is distance? Any questions on that? Okay, so what is distance between X and Y? You have two dots, you want to connect them with some sort of trajectory line, and typically you're connecting them with a straight segment for simplicity. And this distance would be called Euclidean distance, okay? And Euclid, more than 2000 years ago, developed the distance, square root of differences squared. This is the distance that we typically call distance between 2 points, okay? You have two coordinates, you can find how far away these points are by straight segment, straight ruler between them. But you have different kind of distances as well. For example, you want to move from point X to point Y in the city. You can't go straight through the buildings. You need to go around. So typically cities are built with perpendicular streets, okay, more or less, approximately. So you need to go distance which is called city block distance for that reason, because you go only vertically or horizontally by the streets, whatever it is. So your distance will be how far you need to go using only rectangular system of coordinates, which is vertically or horizontally, okay, like that. Now, interesting thing is that it doesn't matter through which turn you turn, like on which street you turn, if you turn between these 2 points. So you can go that blue trajectory, or you can go, first of all, straight here and then turn, or you can go here and then turn here and then turn here, there, and there. It doesn't matter. The sum of the segments, if this is rectangular grid, the sum of the segments will be exactly the same, no matter what trajectory you go between X and Y on this grid. Okay, so it's like distance on the grid. It's also called Manhattan distance, because specifically Manhattan is built in these rectangular blocks. Streets are very perpendicular in Manhattan, so it's called Manhattan distance or city block distance. Okay. You have also other kind of distances. Let's say you need to fly from one side, from Europe to United States, something like that. And if you're looking on the map, which shows you like how you fly, typically airplanes, they have that screen showing you trajectory on which you fly, it will look something like that. It will not look like straight line. And it's obvious why it's not looking like a straight line, because Earth is not exactly flat, okay? Unless you're a flat earther. So you need to fly practically above the Earth on the semicircle, kind of semicircular trajectory. And that will look like that on the two-dimensional map, okay? Because you need to flatten it to show it on the screen. So this is actually the shortest possible trajectory, and this trajectory will be called geodesic distance. Geo is like Earth, okay? Geodesic means the shortest distance on a surface. The surface has particular shape, whatever it is. Earth is almost spherical, not exactly, but approximately spherical. So you go on the sphere. But you could have any kind of shape in 3D. You can go trajectory on that shape, whatever that shape is, to find the shortest distance on that surface. Okay, this is called geodesic distance. Now you can define also distances between more complicated things, let's say between two curves. How do you define distance between two curves? It's tricky. There are multiple ways to define that. We will see some of them. But again, distance is very ubiquitous thing, and you can define it between multiple different things. Okay, and distances are used almost everywhere in engineering, even if you don't call it distance. Okay, so we'll talk a little bit about different definitions of different distances. So this is formal definition of what distance is. Distance function in math. And pay attention, this is not the same as distance in common language. Not always the same. I mean, typically it's close or same, but not always. Because I will show you examples of distances that we would consider distance. in normal language, but they're not mathematical distances. They are just something else. Okay, they are not metrics. So mathematical distances are called metrics. All right, so if you see anywhere in literature that they say metric such and such, this is just distance, okay? Mathematical word for distance. So if you have some particular set, and this is very abstract right now, we will get to particular examples in a second. If you have particular set and the function d, which is distance function, is defined on set times same set, okay, we'll see why, because we need two variables, two inputs. So it's a function of two inputs, and each input is coming from the same set. And this could be set of numbers, it could be set of other things, okay? And it defines it in interval from 0 to infinity, which means distance is always non-negative, obviously. This function should follow 4 different properties. And this is how it is actually defined. So everything which follows these 4 properties, you can call it distance function or metric, all right? So for any x, y, z in that set, so you can think about vectors, let's say vectors x, y, z, or numbers x, y, z. This is the first rule, which is non-negativity. Distance must be non-negative. Sounds obvious, right? All distances are positive or 0 between any kind of objects, whatever they are. And again, objects might be vectors, might be curves, might be numbers, might be all kinds of things. Set is very generic way to say anything about objects. Second property is uniqueness of 0, which means that the distance will be 0 if and only if they are the same, like the inputs are the same, x equals to y.
Same point.
Same point. Like from point to itself, the distance is 0, it's obvious, but this is the only possibility for distance to be 0. No other point will be distance 0 from that particular point. Okay, this is the only point itself. And symmetry, which means if I go from point A to point B, it's same as going from point B to point A, the other way around. Okay, this is third property, and the last one is the most important one. It's triangle inequality. Do you remember the other name for triangle inequality? We discussed that for norms some time ago. It's Minkowski inequality. So the idea is very simple. If you need to go from point X to point Y, and then you go from point Y to point Z, it's shorter to go directly from X to Z. At least not worse, okay? It could be same if they are collinear, okay? But it's not worse, okay? So the shortest distance between 2 points is the direct trajectory between these 2 points and not going through some other points, which is also obvious for distances, for definition of distances. In that case, distance from X to Y plus distance from Y to Z will be larger or equal to distance from X to Z. It's triangle, so you can think about that as, again, each side of the triangle is shorter than the sum of other 2. This is the meaning of that. Okay, whatever the distance is, it doesn't matter. Okay, but we will be able to define in regular language distances which are not satisfying that. Which you might think like difficult to find, but it's not that difficult, really. We will see some example. Any questions on that? So this is definition of what distance is. Distance is any function which is satisfying those 4 properties. Okay, and now we can see some examples of that. So vectors in linear algebra are like that, okay? And distances, Euclidean distances between these vectors are distance functions, okay? This is a Euclidean distance for regular 2 points. So you have points x1, x2, then you have second point y1, y2, okay? You can put transpose here if you want it to be regular vector. All right, so Euclidean distance is computed as square root of square differences. Practically, you don't need that absolute value here because square of anything is always positive. And absolute value squared is also positive. But I'm using that if you want to use complex numbers, because if x and y are complex vectors, then square of complex number is still complex number, and you need absolute value of it, of the complex number, to make it real number, okay, real positive number. So this is why you have just absolute value here. This is only for complex values. For real values of x and y, you don't need it, okay? So this is Euclidean distance, which is computed by Pythagoras theorem. This distance is z1 squared plus z1 squared. This is a distance squared. And we'll call it dE, Euclidean. Okay, familiar with that one, right? It's not news to you how you define Euclidean distance. Okay, city block distance. It's also mathematical distance. And this is sum of that distance and that distance. As I mentioned, if you go like with zigzags like that, you'll get exactly the same distance. It's easy to show, so why not to use just simplest ones, which you have already, which is y1 minus x1, y2 minus x2, you add them together, absolute values, you get the distance, which is how far right and up you need to go total. All right, so far? And again, as I mentioned, it doesn't matter which trajectory you take, you get exactly the same thing. You can actually compute it block by block. Maximum distance, it's also distance, which means you're picking just maximum out of these two differences, okay? This is max of this distance and this distance. Like, what is the farthest single dimension distance you need to go to get to the right location of your second point, all right? This is also distance, mathematical distance that you can define. So how can you generalize it to vectors? And vectors is just a bunch of points. Before that, I showed you just regular two-dimensional points, but you can generalize it to any dimensions, like in linear algebra. So you have vector of n points. So you have x1, 2, 3, 4, 5 through n, all right? And you want distance between these two vectors. So it's almost obvious. You're just adding more of the terms of the same kind, okay? So before that, you had that kind of Euclidean distance. Now you have y3, y4, y5, y55, whatever number of dimensions you have. Just add them under the square root. That's it. This is how you generalize Euclidean distance in n-dimensional space, okay, for vectors. This is how it goes. So the generic formula will be something like that. It's like from I to n, which is n is number, like size of the vector, number of dimensions. You're just doing yi minus xi, and for n equals 2, it will be regular two-dimensional space. For n equals 3, it will be Euclidean distance in three-dimensional space, but you can do that for 50-dimensional space as well, if you want to, okay? Same thing. And this is how mathematicians like to generalize things. They figure out pattern of some kind. So they have examples like for 1, 2, and 3, and they want to generalize it to 1 million. They just follow the same pattern and they describe new thing which works for any number of dimensions. This is how mathematicians like to work and invent new things. So city block distance, again, you had sum of two differences. Now you have more dimensions, which is like y3, 4, 5, 6, 7, and so on, next same thing. You just add more of them, okay? So you'll get sigma from 1 to n of all of these differences. Again, same thing, just generalization to more dimensions, same formula. Maximum, again, you did maximum between two dimensions. Why not to do that for more dimensions, same thing. So you're taking maximum of more elements of the same kind, and this will be the generic formula for that. Okay, for all I. You're picking the biggest distance in particular dimension, this will be your maximum distance, okay? And you have many more like Riemannian metric, Hamming distance, which is used a lot in coding theory, graph metrics, and you have proof here, for example, that Manhattan distance is actually distance based on these rules. I don't know if I want to go through these details. It's better maybe, I mean, this is theoretical, so you have the proof, which is like showing that obviously the difference between these two things is positive, right? Because it's absolute value. So if you're summing absolute values, clearly they will be larger than zero, right? Or equal to zero if all of them are zero. Okay, this is the only case. So second one, you can prove that sum of absolute values is always larger or equal to absolute value of each one of them, like sum of all of them, right? Remember that rule? That like A absolute value plus B absolute value is larger or equal absolute value of A plus B, something like that. So this is coming from that rule, because you're adding absolute values, right? So they clearly will be bigger than A1 minus B1 plus A2 minus B2 plus A3 minus B3 and so on, which is sum of all of them together. So the only way that thing will be zero is when each one of them is zero. Because even if one of them is not zero, sum of something positive plus everything else zero, it's still positive. Doesn't matter, right? So the only way that all of these differences will be zero, and then you get that zero. And this will mean that thing. So they are zero only if AI equals to BI, right? This is the only way absolute value will be zero. And the other way around, you're proving it the same way again. If A equals to B, then this thing is zero, sum of zeros is zero, so you get that thing back. Now, you can switch between A and B because absolute value of difference is the same as absolute value of minus that difference, right? So you can switch the order of A and B inside the sum, and you get exactly the same result, okay? So this is why this is true. This one is more tricky. So for this, you need to do some trick here. So what you need to show is that the distance from A to B and distance from B to C, sum of the distances is larger than distance from A to C. Okay, this triangle inequality. So to do that inside of the absolute value, let's say you're starting with the first one, which is A minus B. And then you need to show it from A to B and C. So you do A minus B plus B minus C, which will be A minus C. Okay? So you're kind of adding the same thing and then you're subtracting the same thing. And then what you're doing, it's absolute value of A minus B plus B minus C is same as equals to A minus C, absolute value, right? But it's always larger or equal A minus B plus B minus C, because again, same rule. Let me write it, okay? Simpler to understand. So you're saying that A minus C for each one of the indices I. So I'm just writing one of them, okay? It's equal A minus B plus B minus C, right? And this one is equal A minus B plus B minus C. And then I can divide that into something like that. So it's smaller or equal A minus B plus B minus C. Okay? And this is true for each element, for each I index. Okay, so you have proven that A minus C, the distance from A to C, is always smaller than sum of the distances from A to B plus B plus to C. Okay, so this is exactly the triangle inequality that we are talking about. But you're doing that for each element. So if this is true for each element, then it's true for the sum as well, right? Picture of that. All right. So you can do sigma on all of them, and then you get the triangle inequalities that we are talking about. This is practically the proof of the fourth part. Any questions on that? So this is just rules of absolute values. Okay. Minkowski distance. Share it again. This is practically generalization of all the things that we discussed so far, which is you can put everything in one formula and to get all of these distances together in one formula, and this is Minkowski distance. So let's say you have two vectors, x and y, and then you're defining the distance as root, which is not square anymore, but p through root, okay? Root of order p, I don't know, how do you call that? Which is not square root, but like you have cubic roots, you have
Power four and through
root, or how do you call that?
and through. So pth. I don't know.
Pth root.
Yeah.
I don't know how to call that, but like you have the pth root, okay, of some of the pth powers of the differences, absolute values, okay? Like how this works for all of these distances, and we will call that distance, Euclidean distance, we will call L2. Okay, these are the names, just for you to know the notation. Okay, so L2 distance is Euclidean. And this works when p equals to 2, so you get square root of sum of absolute values differences squared. Regular Euclidean distance. Okay, now, if you choose 1, this will be sigma of absolute values differences. And instead of square root, like order 1, square root is just no root, right? It's the number itself. So you get back your original city block distance, okay, from p equals to 1. And from p goes to infinity, it's kind of infinite root, infinite order of root of sum of that thing. Practically, you'll get maximum distance for p goes to infinity. And you can choose any other p. These are popular ones, okay? L infinity, you have a lot of that in controls using infinity norms. But L1 and L2, L1 you use a lot in optimization because this is making matrices sparse if you're using regularization with L1. And L2 is obviously the most popular distance, which is Euclidean distance, just straight line between 2 points in n-dimensional spaces. Okay, so these are the most popular ones. But you can use L3, L4, L5, whatever, for particular purposes. Never seen anyone using anything above 3, but you can if you want to. They all exist. Questions on that? Okay, so how you implement that in MATLAB, for example? Okay, you want to implement that type of distance function, Minkowski distance, so you need to give it vector x, vector y, which will be just a bunch of numbers, and then p value, okay? So if it is not infinity, if p is not infinity, then you're computing just regular sum of absolute differences to the power of p, and then to get that root, you're doing that power, okay? But if it is infinity, you're just computing maximum of absolute differences. Any questions on that? Very basic code. And here is distance, which is not metric. Let's say you have 3 different readers, so you can think about 3 different functions, whatever they are, and you want to define difference, like how far away they are from each other. And this will be your distance measure. And pretty obvious to define that as minimum distance between
River A to river B, B to C, or we have X, Y, Z, doesn't matter. So from river X to river Y,
D1 will be the distance, right? This is the closest they come to each other. Between Y and Z, you'll have that distance. This is where they're the closest to each other. And this is the closest distance between X and Z. So pay attention that this is not true. The triangle inequality is not true because D1, which is this one, plus this one, is shorter than this one. So the sum of 2, what we call distances now, okay, actually shorter than the direct distance between the 2. So it's not mathematical distance, it's just something that we can think about as distance. That's not metric. All right. So this is one of the examples where you have sum of distances actually shorter than direct distance. And you have other popular distances here, long list of things, mean absolute error, mean squared error, sum of squared differences, cosine distance, Pearson coefficient distance, RMSE, root mean square error type of distance. You have many, many different distances which people define for different purposes. This is just list. You don't need to remember that. Of course, it's just for your just general education. Like you have million of different distances. And now we get back a little bit to norms. And we want to generalize something that we talked about Euclidean norm to other norms. So we talked only about Euclidean norm, which is size of the vector, right? Remember that you're computing length of the vector and we called it norm. Now, norms could be defined in a more broad way, not only as the Euclidean norm. It could be defined using distance function. Okay, so any distance could have practically its own norm in a way. Okay, so we can define it based on the distance functions. So norm in general, in abstract way, is defined by these 4 rules that you have written here. So any function which takes n-dimensional vector and converts it into real number is a norm if it satisfies all of these 4 rules. Okay, and rules are very simple. Norm is always non-negative, and it is 0 if and only if it is the vector itself is 0 vector. Okay, and this is vector 0, not number 0. Okay, x might be vector of any kind. Then if you multiply something by that vector and you're making norm of it, the absolute value of that coefficient could go out of the parentheses of the norm, and then you will have absolute value of alpha, which is scalar, times x, norm, and then triangle inequality. So this should remind you very much what we define for distances. Okay, very similar kind of rules. So what happens is that you can just define norm between x minus y as distance x to y. Very simple formula, so it will always work that way. All right. So if you have some distance between x and y, it will be norm from x minus y because of all of these properties, which are very similar. Another thing that we, I think, haven't mentioned previous time is also very important and very practical inequality, Cauchy-Schwarz.
And this inequality says that dot product between vectors x and y
smaller or equal to absolute value of dot product, which is almost obvious because absolute value is always larger or equal to the number itself, regardless if it is positive or negative number, and dot product is a number, scalar, right? So it's just number, could be positive or negative. So if it is positive, they are equal. If it is negative, the absolute value is obviously bigger, all right? But the actual Cauchy-Schwarz inequality is the second part, the right part, where x dot y, absolute value, is always smaller or equal to multiplication of 2 norms, x and y norms, all right? Very important thing, used a lot, especially in statistics and other fields, where you have Pearson coefficient is basically based on that theorem. And this is why Pearson coefficient, if you're familiar with statistics a little bit, something which people practically call correlation. It's always normalized between -1 and 1. So this is why, because this is the ratio of dot product to norms. This is what Pearson coefficient is. And if you're looking on one of these previous distances, that Pearson coefficient here, that correlation is exactly that. It's ratio of these 2 things. Okay, without absolute value, so it could be plus or minus. And we will define also cosine for any number of dimensions. It will be practical for us to use that cosine later, the formula. So you need to remember that cosine for 2 and 3 dimensions, this will be actual cosine between 2 vectors, actual angle, theta, and cosine of that angle, theta. But we can generalize it to more dimensions, and it will be x dot y divided by norms. Again, norms could be all kinds of things. It's not only Euclidean norms. It could be Minkowski norms. It could be some other norms, what norms, whatever they are. Okay, so it's like very generic. It would work for any kind of norms. And obviously, you'll get different angles in that case. So even definition of angle will be different. And here are examples of standard norms. You have Euclidean norm, as you expect, and we will call it 2. You remember L2, okay? L1, this is Manhattan norm, city block norm, which will be just sum of the absolute values, maximum norm, which is x infinity. And again, in robust control, we use infinity norm all over the place, like all the time. H infinity, all of that stuff is, all robust control is built on that. So this is just max of all of the maximum of the all of the absolute values of vector x, and this is Minkowski, which is p, and generalization to all of the above. All right, these are standard norms. So now we get kind of back to the definition of lenses, volumes, and areas, as I promised that this will be the topic of today's lecture. After we learned a little bit about how we measure distances, we kind of turn back and get back to like how we measure different things and how we define different things. Back to Euclidean distance mainly. So in Euclidean space, length of particular interval will be just x1 minus x2 absolute value, right? This is straight segment between 2 points x1 and x2 in 2-dimensional space. It will be just difference between these two numbers. Now you want to measure area of a triangle, 2-dimensional space now, okay? And you have some particular points, x1, y1, which is that corner, x2, y2, which is that corner, and x3, y3, which is that corner. And we will call these points P1, P2, and P3 for convenience, just that each point will have those 2 coordinates in it, okay? And I'm defining these P values just because later we will want 3-dimensional thing, and then P will be x1, x2, y1, and z1, okay? So this will be P1. Just for notation, remember that P is point which includes multiple values. It's like a vector, all right? So P is vector, and these are coordinates of the vector. And pay attention also that I'm going in the counterclockwise, which is positive trigonometric direction, transversing these corners, okay? So I'm going P1, P2, P3 against the clock direction. And this will be the area of that kind of thing. We can prove that, but I don't think it's useful for you to see it. It's coming from all kind of geometric theorems. But this is the area. Looks complicated, right? It's some absolute value of 1/2 times all kind of pairs of multiplications of coordinates in weird order, okay? Practically, it's all kind of combinations with plus and minus signs here. Some of them are plus, some of them are minus, like half of them practically plus, half of them are minus. And then you have pairwise combinations of x's and y's, right? All of them. Complicated. So you would not probably guess where that thing is coming from, right? You cannot guess that kind of formula. And you have 3-dimensional, same thing, also 3-dimensional triangle, if you wish, tetrahedron, which is building block for all of the measurements of areas of triangulations in space. So people using triangulation to measure different areas, right, between different points, mesh of some kind, and they build it from triangles. But in 3-dimensional spaces, they build it from that type of structures, which are tetrahedrons, pyramids, practically speaking, okay? So you build space, you can combine multiple pyramids and build any shape you want on a point-by-point basis, okay? On particular grid in 3 dimensions. So how do you measure volume of that kind of pyramid? This will be 1/6 times all of the combinations of 3 coordinates, okay? Again, when your coordinates are P1, P2, P3, and P4. Okay, these are the 4 points that you have to the pyramid to build that pyramid. And each one of them will have 3 coordinates now, it's 3-dimensional space. It could be oriented any way you want, okay? You have probably like 20-something terms in that kind of thing, which is definitely not guessable. And simple question here, not very simple maybe. What should be the condition for vectors x, y, and z? You have 3 vectors that they will create just triangle. You understand? You have like three two-dimensional vectors. Like in 2 dimensions, you have one vector, another vector, third vector. So what should be the condition on these vectors? That they should create triangle. Because general 3 vectors obviously will not create triangle, right? It could be like one way, another way, third way. So it's polygon of some kind. It will have 4 sides typically.
Like that, 3 points?
Intersect, how they can
Not
intersect?
all 3 of them, but they need to meet.
Remember that vector, it doesn't matter where you started, so initial point doesn't matter, so you can
Move it in space anywhere, that's the same vector when you move it in space anywhere. So we typically use 0 as the initial point, like origin for the vector, but it could be anywhere. It's same vectors. Okay, vector has only length and direction. So you want these vectors to have some lengths and directions, and what should be these things? Like what would be the condition that they will build something like that?
Something called eigenvalue cannot be zero.
Has no relation to eigenvalues.
eigenvalue means that
The vector will just scale and will not
Oh, yeah,
change the end.
some of that has to equal the third side.
Sum of angles has to be 180.
sum of angles needs to be 180, but you don't have angles. I mean, you can compute angles of the
Vectors technically, but this is complicated condition. Anything synchronous on that?
Just as simple as x1 can be x1 can be equal to x2, but like I don't know how to say, but basically you can't. Not all the points can be equal. I need a more mathematical way of saying.
Now 2 points are, well, yes, sure, but this is not sufficient condition for triangle. So pay attention that the first 2 vectors could be practically anything.
Third one has
So
to
what should be the third one to close the loop?
go from.
It has to come back to origin, to the original point. So what would be the condition? The last one will come back to the origin, to the first point where you started. Actually, very simple condition. This is a condition. The sum is 0 because each one sits on the tail of the previous one. Okay, so you have like one vector, whatever direction, be anything. Then you start from here. You put in second vector, whatever direction, length, whatever you want. So for them to create triangle, right? So you have this 2 now. You need to go from here to the tail of this one. This sum of these vectors will get back to the 0 point. That's it. This is a condition. Okay. So we will not go through. I mean, if you want to see proof, this will look something like that. Okay. I think I published that already online, that kind of proof. The idea of proof is relatively simple, but it's analytical geometry. So you have triangle, and area of triangle is 1/2 of the base times height, right? So the height is from that coordinate to here. You can compute using that formula, which is analytical geometry formula, from given point x3, y3 to the base between x1, y1, x2, y2. So you can find that length, which is absolute value of this thing. Then you're doing some long computations, solving system of linear equations. I don't think this is relevant or important for that particular lecture, so we will not go through the proof. The idea is that you can compute that formula that I showed in absolute value, which is 1/2, and all this 6 terms or whatever, 4 terms of x1, x2, and so on. So now we want to connect all of the 2 determinants. And first I want to define what determinant is. I mentioned for second dimension, for 2 dimensions, what determinant is. But now we want to generalize it to any number of dimensions, okay? And as I said, the punchline will be, well, all of these areas are practically that same, okay? Volumes, areas, lengths, all of it, okay? So let's say you have matrix with all of these elements A1, A2, B1, B2. So determinant of that matrix, of 2 by 2 matrix, and it's defined only for square matrices, is main diagonal multiplication minus secondary diagonal multiplication. This is how determinant of 2 by 2 is defined. That's what A1 B2 minus A2 B1. Okay. So we will write determinant like that or like that, which is looks like absolute value on matrix, but this is not exactly because it could be also negative. This value could be negative, determinant could be negative. So computation of higher order determinants is computed using second order determinants. You kind of reducing the order each time. How to know how to reduce that order? We need to define something which is called minor of a matrix. And again, this is terminology from linear algebra that you need to understand to compute determinants. So minor of particular element Aij of the matrix is computed very simply by scratching that column and row of that element, okay? So if it is like row I, column J, you're scratching row I and scratching column J, and you're keeping all of the rest of the elements of the matrix, and you're squeezing it into n-1 order matrix. Okay, so you get smaller matrix by one column and one row, obviously, right? So this is that minor that we are talking about, and this is how you compute determinants using these minors. So here's how it goes. Let's say you have 3 by 3 matrix, and we will develop that by first row. You can develop it by any row or any column, that determinant. You take in the first element and multiplying it by -1 sum of I plus j. So all of these elements, like first, third, fifth, and so on, will be positive. Second, fourth, all of the, even on the first row, will be negative, okay? So put in this coefficient, which is plus or minus. In that case, it will be plus, because this one is positive, okay? Times determinant of the minor, which would be that submatrix, okay? So it's determinant of that submatrix, which will be A22, A23, because I kind of scratched this one, you left with this thing. So you get that determinant minus A12 times removing that column, that row, left with these elements and these elements, all right? So this will be that second determinant plus A13, removing that column and row, and I left with that submatrix. So computing determinant of that submatrix, again, writing that using the formula, and this will be the determinant, okay, of 3 by 3 in general. As you can see, if I open parentheses here, you have all of the combinations of all of the elements, all of the triplets of combinations of elements, okay? Some of them plus, some of them minus. And this is where these areas and lengths and volumes are coming from. These are the formulas, okay, with particular twist. So here is numerical example. You can go through that numerical example. Typically, you want to develop that by particular column or row where you have a lot of zeros, because this will cancel a lot of things. Because 0 times anything is 0, so you don't care, right? So let's develop that by the last column. So it's 1 times determinant of that thing, okay? Determinant of that thing. And it's negative because this is plus, minus, like chessboard type of thing, okay? So it's 1 times determinant of that one, plus 0 times determinant of that thing, so it doesn't matter. So I skip it, plus minus 5 times determinant, which is the upper 2 by 3 block and lower 1 by 3 block, okay, which is that thing. And now again, I will develop that by first row here because I have 0 here. So it will be -1 times -1 times determinant of 2, 1, 1, 4, okay? And then plus 2 times determinant of 2, 3, 1, 3. And again, computing using formula, get some number out of it. Determinant is always a number. Okay, it could be positive or negative, but it's number. So pay attention if you have matrix of like 100 by 100, and you each time reducing it to lower and lower order by 1 each time, this is horribly long process numerically. computation is a super expensive computation to compute determinants in computers. So typically people avoid determinants unless these are like very low order type of computations. And this is why we learned LU to compute matrix inversion, because to invert matrix, you actually need to compute determinants. All right. So the determinants technically are not computed that way in computers. They are computed through linear equations and all of that stuff from inverted matrices. So it's more complicated than just regular computation of 3 by 3 or 4 by 4 determinant. It becomes very complex for higher orders. A few properties of determinants before we go into back to areas and stuff like that. So determinant of A transpose is determinant of A, same thing. Multiplication of any single row or column of matrix A by a constant multiplies determinant by the same constant. If you're multiplying all of the elements in A by some constant k, then you get k to the power of n. N is number of rows or columns of matrix A, okay, times determinant of A. Exchanging two rows changes the sign of the determinant. Adding or subtracting linear combination, which is like alpha times one row plus beta times another row, and you add in that to third row, is not changing determinant at all, okay? And for square matrices, determinant of AB equals to determinant of A times determinant of B. And here's something that you don't have to remember that, but it's something that will be important for our future thinking about definitions of vector spaces. This is second way as mathematicians generalize stuff. So first way we looked at, let's say you have particular pattern and you're extending that pattern for more dimensions. This is how linear algebra grew to n dimensions, n-dimensional spaces, and eventually infinitely dimensional spaces. And there it becomes very complicated. And these rules do not work anymore in infinite dimensional spaces. But linear algebra was all developed by just figuring out patterns like Euclidean distance. You can do that for 2 dimensions. Similarly to 3 dimensions, like why not to do that for 5 dimensions now, okay? So this is generalization from pattern. Second kind of generalizations that people thought about in linear algebra, and not only linear algebra, in math in general, how mathematicians think. This is kind of insight into how mathematicians think. You have multiple different objects which satisfy the same rules, like norms, okay? You have all kinds of norms. They satisfy same set of rules, all right? How can we figure out what objects satisfy particular given set of rules? So I will come up with particular rules. I will say, I'm looking for object which is doing A, B, and C, all right? Figure out all of the possible objects which are doing these 3 things, okay? And I will call that object something mathematical, whatever, okay? So you can think about determinants in that way as well. And this is that way. Figure out such a function of matrix A, whatever that function is. So you manipulate somehow elements of matrix A. And this function will have 3 different properties. Property number 1, when row of matrix A is multiplied by some constant, that function also will be multiplied by that constant, which means this function has a homogeneity function, part of linearity kind of property, okay? Second thing, if A, f, which is function of A, it's not changing when one of the rows is added to another, okay? So you add multiple rows together in any combination you want. So that function will not change anything, all right? That's the second property. And third property, if you're taking f of the identity matrix, you just get 1. That function will return 1. That's it. These are 3 properties. So very surprising thing is that the determinant is practically the only function which could satisfy these 3 different rules. You don't have any other function which would be satisfying all of these 3 properties. This is the only one possible, which is kind of surprising because these are very broad properties, I would say, not very specific. They're not telling you how this function is supposed to look like. All right? But this is the opposite way to define different mathematical functions. You give properties that you want this function to satisfy, and then you're trying to figure out if this function is unique, not unique. Do you have like multiple different functions? So in that case, this is unique. Okay. A few more properties of invertibility and determinant, just for you to know. So all of the following properties are equivalent. A is invertible or non-singular in that case, which means A inverse exists, if and only if determinant is not zero, if and only if AX equals to 0 system of equations has only trivial solution where X equals to 0, okay? And if and only if linear combination of rows is 0 only if all coefficients are 0, if and only if linear combination of columns is 0, only if and only if all coefficients are 0, okay? So all of these properties are practically the same, right, for invertibility of matrix. And we will see even more of that. In that case, none of the eigenvalues should be 0, and you have more properties of invertibility. We will talk about it later, all right?
So the last two properties are independence, linear independence of rows and columns, and we will talk about them
Next week when we talk about linear spaces. Yeah, so another thing that determinants are very helpful with is solving of system of linear equations without going through matrices. And funny thing is that determinants were invented long before matrices, okay, before linear algebra in general. So if you're looking on that guy, Gabriel Cramer, he lived in 18th century, right? 1700 plus. Matrices and all of the linear algebra were developed end of the 19th century, which is 1850s plus, okay? So it's more than 100 years later, after he already developed his way of solving system of linear equations using determinants. The determinants were like way before linear algebra, right? And this system is solved like regular system AX equals to B. This is the system of linear equations. It's solved extremely simply using Cramer's law. And I somehow learned it in middle school when we just started to use systems of equations like basic linear equations, 2 by 2, 3 by 3. And then I was ahead of everyone solving the systems because everyone used Gaussian stuff, like simplifying, moving, and making mistakes on the way. You know, it's very easy to do like computational mistakes when you doing Gaussian elimination approach, right? But this one is extremely easy to compute, especially for 2 by 2 or 3 by 3 system, especially if you have some zeros in the system, okay? Here's how you do that. You want to compute x of j, which is j's element in the answer, okay? The variable that you want to find. First of all, you compute in determinant of matrix A. If it is 2 by 2, it's just main diagonal multiplication minus the secondary diagonal multiplication. That's it. It's like multiplication of two numbers minus multiplication of two numbers. Very easy to compute for 2 by 2 systems, okay? So you compute determinant of A. Then you compute determinant of modified A. And that modified A, you just replace column J by B. Same matrix A, but you replace in one of the columns with B, which is that free coefficients in your linear system of equations, okay? So if B replaces first column, you get x1. If B replaces second column, you get x2. If B replaces like nth column, you get xn. That's it. So you dividing determinant of Aj, which is that modified A, by determinant of A, and you get your answer. As simple as that. Very simple, right? Like, techniques are very easy here, very simple. The only problem here, again, when you need to compute system of 100 by 100, and then computing determinants of that type of system is headache. You cannot do that. You need other numerical techniques to do that because it's infeasible in normal time. But for smaller systems, like in school, this works perfectly. And also, you know that you will have only single solution if determinant A is not equal to 0, as we mentioned. So A is invertible in that case. But if it is equal to 0 and exists such J, the determinant of AJ equals to 0, so it's like 0 divided by 0, you can have infinite number of solutions, because 0 divided by 0 is not contradiction to anything. 0 divided by 0, if you remember, it could be any number in regular algebra, okay? So actually in calculus and algebra, people do not even define that. But in calculus, you define like 0 divided by 0 is undefined, but could be anything. So it's infinite number of solutions. It could be all kind of. But if you have determinant of A equals to 0, and for any other AJ determinant is not equal to 0, then you have just no solutions, right? Because it's something which is not 0 divided by 0. And it's not, you cannot do that, right? So there is no solution to that kind of thing. So even from that simple representation of determinants, you can understand how many solutions you will have, all right? This is very easy way to see it. And here is a simple example. Oops. So this is a system of equations. The matrix A will be 2, 3, 7, minus 5. B will be 8 minus 3, which are free coefficients in the system of equations. And then this is regular determinant of that matrix, which will be 2 times negative 5, so it's minus 10, minus 21. Okay, so it's minus 31. And here you replace the first column with B, which is 8 minus 3, and this column stays as is. So you do 8 times minus 5 minus 3 times 3, and you get 1. Okay, so practically this is x equals to 1. And y, same thing, you just replace in the second column with B, computing this number is still minus 31, this one is minus 62, so the answer is 2. So x and y equals 1 and 2. Done. Okay, no Gaussian an elimination of any kind. So it's very simple, not tricky thing. And now we are, let's see. Okay, we still have a few minutes, so we can just, I will give you where these formulas are coming from, okay? So this is length, x1 minus x2, this is length of that segment. And this, just to mention what you've seen before, you have that length. This is area formula. This absolute value will be the area, and this will be volume. And here, how you get there, okay? So look at the pattern. So if you have segment, it's x1 times 1 minus x2 times 1, which is practically x1 minus x2. And if you're taking absolute value on that, you get your distance. And it's 1 divided by 1, so it doesn't matter. For the second formula, you need to compute that kind of determinant and to divide it by 2. So it's 1/2 of absolute value, whatever the formula you had before, that value, all of that stuff, okay? You can write it that way. So it's x1, 2, 3, y1, 2, 3, and 1s as the last column, and 1 divided by 1 by 2. This is the volume formula. Again, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, column of 1s, 1 divided by 6. 1, 6, it's 1 times 2 times 3. Like you can already guess how we will expand it to 4th dimension. So you'll just have, obviously, 4 by 4 matrix will become 5 by 5 matrix. Last column will be column of 1s. Z, you will add maybe some W or additional variable. It will be also 1, 2, 3, 4, 5 in that case, okay? And here you'll have 1 times 2 times 3 times 4. Okay, so it's 4 factorial. Remember what factorial is? It's like multiplication of all of the numbers up to that number. So it's like 1 factorial, 2 factorial, 3 factorial, 4 factorial, into 100 factorial, whatever. Okay, so this is generalization of length, area, volume, hypervolume. Okay, so hypervolume will be like just bigger matrices, but same thing. All right, any questions? Okay, thank you. We'll continue next time.